Okay, so now we are coming to the next speaker of our session, and we welcome Iris Paparelle from Italy, Trieste, and she's representing the National Research Council of Italy and Institute of Optics. Iris will tell us about this very important element, the key distribution that was mentioned in our big introduction today, and she will talk specifically about the direct communication. Okay, welcome, Iris, and let's hear the talk.
Hi, I'm Iris Paparelle, and I'm from CNRINO, which is a lab in Trieste, Italy, and I'm going to talk to you about an introduction to quantum communication, a history of sharing secrets and keys. So there is much interdisciplinarity in this topic, and I'm going to show to you why would you listen to my presentation. So in quantum communications, there are many things to do, from physics to computer science, engineering, information theory, mathematics, but there are also a lot of other implications of this field, which span from politics to society and ethics. So let's start by understanding what is quantum communication. So first of all, quantum communication is actually secure communication. That means that two parties want to share a secret, so some secret information that a third party should not be able to eavesdrop. This is actually something that we use every day, from protecting our individual privacy to securing public infrastructure. So every time you send an email, you're actually using secure communication. When you use banking, when you want to share some health records between, for example, two hospitals, when you share your own intellectual property, you're trying to secure your data in the transmission from one part to another. So, as you may understand, this is something that is very common in our own lives and is actually already currently done even without quantum. So let's see now how is it done and how it was done in the past. So the first ways of protecting data was early cryptography. So cryptography is the art of starting from a plain text, the text that you want to send, your own message, and transform it into a crypted text, which is not readable directly by ourselves. So we start from a certain message and we apply some functions, some algorithms to it, to the letters of it, and obtain this crypted text, this encoded message. The first one to start cryptography, on the most famous first one, was Caesar, the Roman emperor. So this already shows that one of the applications of cryptography, of secure communication, is also the military one. So if we want to protect sensitive data, such as let's attack this city, I hope not, or let's follow this route, it's important to protect this kind of data from the enemies. So Caesar, his own technique was to take each letter of the message that you would like to send and shift it from a fixed number of letters. So for example, if the key, so the number of letters that is shifted, is 19, as in the first example that I show in this slide, we start from, for example, A for Ave Caesar, and the A becomes actually a T, because it's shifted of 19 letters. The V, let's see, becomes an O, and the E becomes an X. So in these times we have TOX, which is not understandable and not directly linked to Ave of Ave Caesar. So, of course, this was already quite advanced for the barbarians that Caesar has had to front. But we can understand that in the future, after this kind of cipher, some evolutions were made. Also because this kind of cipher is quite easily to break, because the moment that you know some statistics of the message, for example, that all the messages start with Ave, or that, for example, in English the most common letter is E, you can check what is the most common letter in your message and just calculate the key in that way. Then there were some more difficult, very difficult even to break algorithms, such as the Enigma one in World War II, and even one that was proven mathematically to be absolutely secure, which is the one-time pad. So this is why in the title I mentioned information theoretical security. So this is something that means that this protocol was really proven mathematically to be secure. So with some specific quantities such as mutual information, so some statistics, we can show that this kind of algorithm is perfectly secure. The one-time pad works a bit like the Caesar cipher, actually. We start from a plain text and we apply some shift, except that the shifts are random, not always the same. And if we respect some conditions, such as the plain text being as long as the number of keys, the keys being absolutely random, we are sure that the ciphertext is unbreakable. Of course, these two properties that I mentioned, for example, are very difficult to implement because through randomness and also having keys so long as the message is very time-consuming and money-consuming, so it's never actually applied. So in the next slide, we're going to see what is the current state of secure communication. Our current solution is computational security, so not mathematically proven to be secure, but still computationally difficult to break. In fact, it works like this. We take a message, X, a kind of data that we want to protect, and we apply to it some function, some algorithm like RSA or the other one that the elliptic curve digital signature algorithm that I mentioned down here, or many others. And we apply this kind of function to the message, which gives us an output. This is very easy to do in the sense that it's like locking something with a padlock. You just close the padlock. But then if you want to come back later to the original message, you need a key. Why? Because to open a padlock, you still need a key. So these functions are in a sense asymmetric. So it's easy to go from x to f of x, but then coming back, you need some other information, which we call usually a key. So, of course, if we imagine a padlock, we can always go brute force, like spending a lot of energy to break it, but in the end, maybe we can do it. This is very difficult usually. It takes a lot of time and it takes a lot of money. So, of course, if you want to, for example, steal a credit card and it takes you for your computer 1,000 years, it doesn't make sense for you to steal that credit card in that way, in that brute force way. And there are, for now, no available, no efficient computational algorithm to break this kind of padlocks in an efficient way. So, well, why do we need quantum? What can quantum do to help us in our quantum communication? And why do we want to change our paradigms? In fact, what is happening is that there is a quantum threat, in the sense that quantum computers, but also supercomputers, are threatening this kind of algorithms. So, because I said that computational secure algorithms are computationally difficult to break, but there is no rule, no law, no mathematical proof that says that they are unbreakable. Most of them are just difficult for our actual state of computation. So with quantum computers that can use qubits instead of classical bit, which maybe you have heard in other presentations or later, they can calculate in a different way and even be much more faster than classical computers. So this has led to a sort of quantum race in Italy, but also, of course, in Europe, in China, in the United States, and in many other states. There is a sort of quantum fever of creating the most advanced technology in this sense, and to prevent that some malicious actors arrive to this kind of technology before governments, for example. So as you can see, in Europe, for example, there is the Quantum Flagship Initiative. They also wrote a quantum manifesto to really establish a roadmap for quantum technologies. This kind of information that I just gave you express also a need of regulation and transparency, that we have to be really aware before starting studying this kind of technologies. So first of all, to implement quantum communication, of course, we need physical infrastructures. Yes, we can still use, for example, some fiber links that are already used for internet, for some kind of technologies that I showed you later. But still, there is a kind of technical knowledge and technical infrastructures that has to be created. So these kind of structures have to be national and even international. For example, the backbones of fiber that rely one city to another. So of course there is a need of collaboration. Also because, for example, if you want to communicate, you can't expect just to communicate in your own country, but you also expect to have like a European network of communication, or even more. That's what we hope. Also, we need some collaborative and transparent internet governance model. So of course, we already have some troubles governing the internet network because there is no actual regulation that apply worldwide. This is also what we need to take in account when we imagine a quantum internet, because of course it will share information, and also it will be information that has to be really protected. So we need to be collaborative among the countries and to create a real regulatory apparatus of laws about how to use these new resources. Also, we know that quantum technologies and even quantum communication can be used to gain military and strategic advantage. So not only Caesar 2000 years ago could use cryptography to communicate in a secure way with his soldiers, but also now, of course, if a country develops a quantum computer much more efficient than the other ones, it can attack the other countries, or even if it has some quantum really secure communication, it would be far better if everyone could profit from this kind of technologies. This is why we also have to avoid monopolization of quantum technologies. So to have national and international infrastructures, national and international businesses that manage this kind of technology, so that we don't rely only on a few very powerful businesses and companies. Go back to quantum mechanics. So as I said, quantum mechanics is a threat in a certain sense, but it's also a kind of help because there is quantum communication, and quantum communication is unconditionally secure because no one can violate the laws of physics. So as I told you, there are some algorithms like the one-time pad that are mathematically proven secured, but these are very difficult to actually implement. Then there are the computational secure that are not protected by any laws that can be overcome by any development that we have in the future of computers and quantum computers. And then there is this physical security, which can't be violated, of course, because it is protected by really laws of physics. So what are these laws? First, let's talk about quantum objects, so the objects that verify these laws. So usually they're very little objects or even light. So for example, the light that exits from a laser. So I'm talking about photons, electrons, atoms, ions, and etc. These objects have special properties and laws. The first one that I'm going to talk about is observables. So in quantum mechanics, you can't just observe an object generally, just to know everything about it, but you have to specify what kind of questions you are asking. So for example, if we have an object that has many properties at the same time, for example, shape and color, you have to specify what questions you are posing. And this influences your measure. You're observing the object. For example, in this box, if we ask what are the shapes of the objects in this box, so let's imagine this box is a quantum object, we have our observing and then we have a collapse. In fact, we collapse on the answer that is given to us. So the answer that is given to us is with 2/3 of probability round. The shape is round. The shape of the object is round. And in this way, now when we will look afterwards at the box, we will only find round objects. If instead we asked what is the color of the object and we do our measurement, we have another kind of collapse, a collapse with 1/2 probability on the orange kind of objects. Of course, if after this we redo a shape question, we collapse only on the 2 rounds. So you see that according to the question, according to your observable, you can influence the object. Why? Because of collapse. This, in fact, is due to having more than one property, more than one answer to the question that we have. So this is what we call superposition. So let's try to understand it in another way. Let's imagine that we want to characterize the directions of some arrows. So, for example, we may have a very specific question that is very specific observable, that is the arrow horizontal or vertical? For this, we have like a basis, the violate basis, which is exactly a cross that helps us to determine if an arrow was on the one horizontal axis or on the vertical axis. If instead we want to distinguish between a diagonal and anti-diagonal arrows, we may have another basis. This basis, we call it the yellow basis, for example. And so it is the same observable, but we also have to specify the basis in which we measure. Often in quantum mechanics, you cannot observe the whole span of the possible answer, but you always have to specify kind of orthogonality of the answers that you can observe. So what happens if we observe a diagonal arrow in the violet basis? What we observe is that this arrow for us will be in a superposition. So 50% of probability that I measure that is an horizontal arrow and 50% of probability that I measure it as a vertical arrow. So in this basis, the diagonal arrow is in a superposition of horizontal plus vertical. And when we measure it, as I said, it collapses on one of the two states. And when it collapses, for example, on the horizontal side, I can't really distinguish between a real horizontal arrow and a diagonal that has collapsed on that side. So this is the true effect of quantum superposition. So this is also something that you may have heard as the Schrödinger cat, which is at the same time alive and dead or sleeping. A last property that I want to talk about is no cloning. Then there are many others like entanglement and squeezing, but let's start with no cloning. Let's finish with no cloning. So no cloning is another consequence of quantum superposition. So let's go back to our cat, which is dead and alive at the same time. The existence of this thing actually prevents the existence of a quantum copy machine. So if we construct a quantum copy machine, it actually would be able only to copy only totally black sheets or totally white papers. If we try to copy a superposition, so something that is both black and white at the same time, we can't. We enter in a contradiction. There are like two possible results at the same time which contradict with each other. So because of the Schrödinger cats, we can't clone a quantum state, only very specific ones. So you understand that such kind of quantum copy machine doesn't make any sense. So now, quantum secure communication. We imagine two parties, Alice and Bob, that want to communicate by using quantum objects. So, for example, light or electrons with their spins, atoms, or whatever you want. What actually they don't want is a third party that we call Eve to steal their information, so to read the information that they are sending to each other. So let's see the first protocol of quantum secure communication so that we can understand how to use the properties that I mentioned before to communicate in a secure way. The first quantum protocol of secure communication was actually a quantum key distribution protocol. So Alice and Bob, in the end, they really won't have exactly a message shared between us, but more like a key. So, for example, a sequence of 0 and 1s that they won't have chosen exactly what 0 and 1s, but at the end they have the same. So this is like a normal key. You don't really choose the shape of the key, but it's important to open the same door. And this is also considered as a form of quantum communication. So the protocol starts with Alice sending, for example, some arrows, the same that we saw before, which are, for example, the polarization of light. So we have horizontal, vertical arrows, diagonal and anti-diagonal. So as you already can imagine, the diagonal one will be in a superposition for the horizontal vertical basis and vice versa. For example, the vertical one will be in a superposition for the diagonal anti-diagonal basis. So she sends many states quite randomly to her friend Bob. Bob himself doesn't know what Alice is sending, not even the basis that he should use, so he also measures randomly some horizontal vertical basis, some diagonal anti-diagonal basis. And Eve, in the middle, can try some attacks. We will see them now. What she can do is, for example, try to clone these states and one part measuring herself and the other part sending it to Bob. But because of no cloning, she can't really intercept and resend anything. She also can't measure the states because, as Bob, she doesn't know the basis. So if she measured with one non-orthogonal basis, she will read an incorrect 0 or 1. How can Bob instead get some information because he also doesn't know the basis? This is done by confronting Bob's choice of basis and Alice's initial choice after sending the key, after sending these states actually. So first we use the quantum channel, we take advantage of the fact that Eve in the middle can't do anything, and after that the states are already been sent, so when Eve can't do anything, Alice and Bob confront themselves. They confront themselves on the choice of basis. So of course, also this is irrelevant information for Eve after the transmission of the quantum states. But for Alice and Bob, it's very interesting because Bob can know when he chose the right basis and say, okay, so this was the right basis, tell Alice, and know that the measurement that he obtained in that case was exactly the 0 or 1 that Alice has sent. And this way, in the end, they have a true key by 0 and 1s that they can use for sharing a message or something like that. So this is proven to be secure, and all the protocols of quantum communication in general can be proven to be secure in many ways. So either experimentally, which is the ending stage of usually testing a protocol, or with numerical simulations or theoretical calculations. So in this way, you can see that even mathematics, information theory, and computer science and engineering are very important. So the quantities that are usually used to prove, at least theoretically, that a protocol is secure are the ones that I listed below. But of course, this is just a test of the protocol. Then you can experimentally prove that it's secure. So now just a little zoom on what information carriers we can use. So as I said, for example, the light, which is composed by photons, and the polarization of light can be used as the arrows that we talked about before. Light actually has many other degrees of freedom that we can exploit. For example, the path in which a ray of light passes, the amplitude, and the phase. I myself, I use the amplitude, by transmitting light in optical fibers. So the same, with the same wavelength that you use for telecommunication. So this is my lab, for example. You can see it's a setup in fibers. So to conclude, I'm going to show you a bit of real-world applications that are done now with quantum communication. So in the banking industry, for creating digital signatures or authentication, in the financial industry, in government and defense, so for data protections, but even for elections, for data centers. So each time that we have to transition some data, for example, for healthcare. And for example, a very interesting field for me is power grid, so protection against blackouts caused by hacking. So here is, for example, an example of grid automation with quantum security. Also, China is already using quantum satellite communication for their power grids. Danske Bank, for example, tested quantum communication. Healthcare data can maybe be protected by quantum security. This is a study of IDQ, which it also celebrates a 10-year anniversary some years ago of the first real-life quantum cryptography installation in Switzerland. And then, for example, in Italy, in Trieste itself, which is my city, there was last summer, the first demonstration of quantum communication among 3 states, so international communication. So thank you very much for listening, and remember, quantum communication is now, so you're invited to study it and ask me questions and inform yourself about this field. Thank you very much.
Many thanks, Iris, for this great historical look at the security and communication. And this provoked quite interesting discussion in the chat regarding fears and also the future of physics paradigm. Iris is with us in the chat, and although she has difficulty seeing the chat, if I understood correctly, so if I can ask Akash to habilitate her in the chat and also make her co-host so she can possibly join better. In the meantime, I will read a little bit of questions, and then Iris may try to answer them to me, and then I will read your answer. So the first question was first thanking from Geta Hon for the amazing presentation, and what you mean by monopolization of quantum technologies, which while Iris will write the answer to me, I will say that probably she already mentioned. Oh, Iris can now unmute. Let's see. Hi, Iris. Great. Thanks to making it. So yes, monopolization.
Okay, so monopolization, I mean the fact that maybe some companies, because of the fact that they have financial means and economical means, they have like the patent for some protocols of quantum communication and or quantum computing, they don't share it with the other world. So for example, the phone, imagine if the phone was not something that everyone could afford and everyone could use. So this is what I mean about monopoly.
Okay.
I don't know if you heard me.
Let's see if more specific questions will come from GitHub. In the meantime, there was another question that actually I provoked a little bit, and regarding the laws of physics that we consider as the security for our communication, shall we make somehow a safety caution saying that there are paradigm change in physics, and one day we may have other physics, like it was from classical to quantum, and shall we be somehow counting on the fact that one day we might discover new laws that might bring a blemish in the security of today?
Okay, well, of course, I don't know the future, so I can't really answer. But the thing is that even for classical physics, yes, we have new paradigm for very specific cases like very cold temperature or very little elements, but still, for example, cars still work. So, or when we make an object fall, they still fall with the laws that we had 300 years ago. So I think that quantum mechanics it's a model that works in some way.
Okay. We also get in the meantime a response from Michela Teodoro, who is actually sharing this point of view with you, that nonetheless the paradigms will most likely change. He believes that even if the new theory extends quantum physics in a direction which does not actually affect this specific application of quantum communication. And then probably to wrap up, we have an interesting share, which is actually rather emotional, but I think we are all people and we should share our feelings. So someone says, for example, that at times he's scared of how unsafe we might be in the future with quantum information. And is it too emotional, or do we all share, or at least Iris maybe also share this kind of feeling?
So, of course, as it is my field, I should say, yes, be worried and change all your credit cards. But of course, I also know that it's a bit of a quantum bubble in this moment, a quantum fever. So even the quantum computation that is so scary for for example, for the RSA algorithm that protects our cards, it's still very not mature. So, and even some people just say, yes, we just need to double the size of our codes, and quantum mechanics is far from being a threat for us, because we have still a lot of problems with qubits. So I wouldn't say worry for yourself immediately, maybe for your children, I don't know.
Okay, the time scale may vary. Thanks a lot, Iris. This was great historical presentation, and I will now stop the recording.